going to try to make a podcast over note cards 40, 41, and 42, graphing rational functions, and we're going to do so using the knowledge of vertical asymptotes, horizontal asymptotes, and we're also going to continue to talk about roots and zeros and things, and we're going to try to put a lot of things together that we've been learning and graph rational functions without using a calculator. So note card 40 talks about vertical asymptotes. A vertical asymptote is a vertical line that a curve or a function, when we graph it, it's going to never cross or touch. It occurs at x values that cause a function to be undefined, or in other words, when the denominator is equal to 0. So if I have an example, f of x is equal to 2 over x plus 3, there's going to be a vertical asymptote at the line x equals negative 3, because when you take the denominator x plus 3 and set it equal to 0, you get that x is equal to negative 3. So we have a vertical asymptote. Looking at this graph and trying to make sense of what we're talking about here as far as these limits are concerned, how do we read these? This says the limit of f of x, or this function, and this function, I will kind of put my highlighter on it, is this piece, and this piece. And these vertical lines should actually be dotted. These are my vertical asymptotes. And these vertical asymptotes, the curve or the highlighted portion will never touch or cross. Okay, so let's read these limit statements and how they make sense. The limit of f of x as x values approach a from the left, okay? And this a value is actually going to be, well, actually I read it from here, because here we're saying the vertical asymptote exists at x equals 2. These up here are actually the general form where a can be any x value. These limit statements down here apply to this actual graph, because we have a vertical asymptote at x equals positive 2, and we also have a vertical asymptote at x equals negative 2 as well over here. So how these limit statements are read is the limit of f of x, or this function, as x is approaching 2 from the left. So if we're talking about right here, this line here, if I'm approaching 2, that's this piece right here. So as the function is approaching 2, as it's getting closer and closer to 2, and remember we're reading this graph from left to right, as I get closer and closer to 2, this graph is going to go off to infinity. It's equal, the limit is equal to infinity, because as I'm getting closer to 2, this graph is never going to touch this vertical asymptote, because remember up at the top of the note card it says on vertical asymptotes the function will never cross or touch. But as these x values get closer to 2, this function f of x will head off towards positive infinity up here. It would continue to go up in that direction, so it's equal to infinity. As the limit of f of x is approaching x, as x is approaching 2 from the right, this means it's approaching from the right. This minus sign over here means that it was approaching from the left. So as x is now approaching from the right, so I'm going to the right, and as x gets close to 2, my function is heading to negative infinity. And so that's how you would read those limit statements. We won't be working with limit statements a whole lot right now, but it is important that you do know how to read them, or at least have seen them by the time you get to calculus. And we will work with limits a lot more towards the end of this school year. We'll put a lot of work in on limits. So now the limit as f of x as x is approaching negative 2. Now I'm over here on this line x equals negative 2, this vertical asymptote. So as x is approaching negative 2 from the left, so that's from the left, as I'm approaching negative 2 from the left, the limit is negative infinity because this is heading off towards negative infinity. Now the limit of f of x as x is approaching negative 2 from the right. I'm approaching negative 2 from the right, and as I'm approaching negative 2, it is heading off towards positive infinity. So that's how you would read those statements. But the most important thing that you take away from this note card is not so much the limit statements right now. These limit statements are very new to you, and we're not really going to be focusing on those things right now. The most important thing that you take away from this note card is how to find the vertical asymptote. And the vertical asymptote is found by setting the denominator equal to 0, and whatever the x values are, those are your vertical asymptotes, and they're drawn with dotted vertical lines. Now let's talk about note card 41 and horizontal asymptotes. A horizontal asymptote is a horizontal line that a curve gets very close to but does not usually cross or touch. So on vertical asymptotes, going back to note card 40, vertical asymptotes, the function will never ever cross or touch a vertical asymptote. The difference with horizontal asymptotes is that they usually do not. Sometimes they do, they usually do not touch or cross a horizontal asymptote. So it says sometimes a curve will cross a horizontal asymptote, so that's just to kind of let you know. A line y equals b is a horizontal asymptote of f of x if, and we have these limit statements again. So here we're saying that right here, looking at the bottom statements, again, these statements are more of a general for any horizontal asymptote. These are for this one because the line y equals 0 is what appears to be my horizontal asymptote here, or the x-axis. So this says the limit of f of x as x is approaching negative infinity. So as x is approaching, as I'm getting closer to negative infinity going to the left, you'll see that my function, as x is approaching negative infinity, my function is approaching the line y equals 0. And as the limit of f of x as x is approaching positive infinity, or in other words, as I start going to the right on my function as x is approaching positive infinity, this function looks like it's getting close, close, close to y equals 0. And so that's how you read those. Now let's move on to note card 42. And I have up here 41, but it's actually 42. So this is the note card where we're going to actually look at graphing these rational functions. And we're going to be talking about several different things to enable us to do this. Two of those things are going to be the vertical and horizontal asymptotes. Number one says, if possible, factor the numerator and the denominator. And so as we look at this, we just have a set of instructions here on how these work. And let me create myself some space and let's work an example as we're reading through this. Now, I'm not going to be able to click off of the screen to scroll down with my note card like you can. And so, as I'm just going to keep this up because if I click off of this, our graph is going to disappear as we're moving along. So let's see how this works out. Just read along with me on your note card and your note card notebook as I'm working this problem. So the example that I'm going to use is one of our homework problems. And it's y equals So the first step says, if possible, factor the numerator and the denominator. So the bottom should be easily seen that it's factorable. That's the difference of squares. So I have x plus 6 and x minus 6. And the top, if I'm looking for two numbers that add to get me negative 7 and multiply to get a positive 6, signs are the same, they're both minus, should be x minus 6 and x minus 1, because negative 6 plus negative 1 is negative 7, and negative 6 times negative 1 is positive 6. Okay? So I was able to factor something, and it says if any factors cancel. Well, they do. And we're going back to our previous two assignments of multiplying and simplifying or dividing rational expressions. You should see that the x minus 6 factors cancel. And it says if any factors cancel, go to step 2. So step 2 says if the factors cancel, then the function has holes. Set the factor that cancels equal to 0 and solve for x. Put the x value into the equation and find the y value. The x and y values are the coordinates of a hole. So a hole is going to be a little spot. So if I take my factor x minus 6 and set it equal to 0, x minus 6 equals 0, I get that x equals 6. Now what I want to do is to find there's going to be a hole. In other words, if I have a graph, let's go over here and just look for a second. Let's say I have some function, and it's just some curvy function, and right here I have a hole. This is a hole. It's one coordinate where the function is not going to be defined, and because I have two factors that are going to cancel out here, I have one of those in the graph that in the function I'm about to graph. And the way I find that is the two factors that cancel, or the factor that cancels itself out, I set it equal to 0 and solve for x. What I want to do now is, see, I'm looking for this ordered pair. This is an xy value. I have the x value of it right here at x equals 6. I need the y value. How I find that is, after these factors cancel, what I'm left with, create myself a little bit more room. What I'm left with is y equals x minus 1 over x plus 6, because these two pieces canceled. So you go to this function with what's left and plug in x equals 6 and then solve for y. So we have 6 minus 1 over 6 plus 6, which is 5 over 12. And so what happens here is that this hole, I'm going to have a hole that exists at the ordered pair 6, 5 over 12, or almost 1/2 for the y value. Okay? So just hold on to that piece of information. I'm going to have a hole there when I start to graph my function. The next step is to find the x-intercepts. The way we find our x-intercepts is we set our numerator equal to 0 and solve for x. And so I take my numerator of what's left, I have x minus 1 equals 0. And so I get that x equals 1. So my x-intercept is going to be x equals 1. Okay? Now to find the y-intercept. Number 4 says to find the y-intercept. And the way we find the y-intercept is to plug 0 in for x and solve for y. This is nothing new. We've known how to do this since Algebra 1. So to find the y-intercept, take my function of what was left, this, after the hole came out, and I want to put a 0 in for x and solve for y. So I have y equals 0 minus 1 over 0 plus 6, which is negative 1 over 6. So my y-intercept is negative 1 over 6. Step 5 says to find the vertical asymptotes. And the way we find our vertical asymptotes is to set the denominator equal to 0. I'm going to have to start over here. Okay. And I know some of those things erased. Just bear with me just a second. Okay, so far, recapping so far what I found that I have a hole, not a W hole. A hole at the ordered pair. What was the ordered pair? 6 comma 5 over 12. Okay. I also found that I have x-intercept at 1, right? And I have a y-intercept at negative 1/6. And vertical asymptote is where I'm at. So the function that I have left, once that hole comes out at the beginning where we canceled the factors x minus 6, the x minus 6 was what canceled. And then what we had left was y equals x plus 1 over x plus 6, right? Minus 1. Okay, so this is where we're at so far. With the first few steps, I found that I have a hole at this ordered pair. I have an x-intercept at 1, and I have a y-intercept at negative 1/6. Okay, what I have left after the factors of x minus 6 canceled, I have this function left. And so to find my vertical asymptote, I set the denominator equal to 0 and solve for x. So my denominator, finding the vertical asymptote, my denominator is x plus 6, so I take x plus 6, set it equal to 0, and I get that x equals negative 6. So I have a vertical asymptote at x equals negative 6. Okay. Now to find the horizontal asymptote, it's a little different, but we have all of these steps here to show us. It says horizontal asymptotes, it's the line that the curve approaches and usually does not touch. We have this notation of our function. F of x equals a times x to the power of n and over b times x to the d. Okay. Now what a is the coefficient of x and n is the power of x. Okay. B is the coefficient of x in the denominator and d is the power of x. Okay. So let's just kind of break this down. Up here, hopefully you can see that a, the number in front of x, is 1. And n, the power of x, is also 1. B, the coefficient of x in my denominator, is 1. And d, the power of x in my denominator, is also 1. Now, you want to write these things down each time and then use this criteria right here to tell you what your horizontal asymptote is going to be if there is one. Okay? It says for n equals d, is n equal to d here? Yes. So we're right here where n is equal to d, right here on this one. Where n equals d, my horizontal asymptote is going to be the line y equals a over b. Or in other words, the line y equals 1 over 1, which is 1. So my horizontal asymptote here is going to be y equals 1. Okay? Now it says to try to sketch the curve. Notice this word try, because sometimes all we can do is kind of give a good guess of what we think this curve is going to do. And so we know some things without a doubt. For example, when I set up my coordinate plane here where I'm going to try to sketch this curve, I know some things without a doubt. Now mine's going to be kind of a rough sketch. I got a 1, 2, 3. And so on. Okay, so what do I know without a doubt? I know that there's a hole at the ordered pair 6, 5/12, or in other words, basically that hole is going to be at 6, almost 1/2. So there's going to be a hole right there, and I can go ahead and graph that hole. I know the x-intercept is 1, where it's going to cross the x-axis is 1, so I'm going to go ahead and put that dot right there. My y-intercept is at -1 over 6. That's about right there. And I know that my function is going to cross the y-axis about right there. I have a vertical asymptote at x equals -6. I'm going to sketch that in black, and you want to also do these in dashed lines. So I have a vertical asymptote right here at the line x equals -6. And I have a horizontal asymptote at the line y equals -1. And I'm also going to sketch that using a dashed line. Now, let's use what we know here from past experiences, from what we've learned this year, to kind of give a good try at graphing this function without a calculator. Here's the things I know. There's a hole here. The function's definitely going to cross here, and it's going to cross here. And so it looks like the function might be taking on the path of here. It's going to maybe approach that as it goes to the right. Maybe it's going to approach that horizontal asymptote, y equals 1. And it's going to come this way, and it's going to go through the x-axis there and through the y-axis there. And since it's bending down, and since I have this vertical asymptote here, it's never going to touch that, so I'm going to think it's probably going to approach this way and go on down to -infinity. And so this is a part of a function that I definitely know I could probably do. Because see, the horizontal asymptote, the function typically does not cross that axis, this asymptote here, so I'm going to guess that it's not going to. We are going to work with some on horizontal asymptotes that it might cross, but we'll talk about that later. Now also, what do I know about this function? Look at the function. What kind of function does this look like? Remember our reciprocal function from the beginning of the year, where we had 2 pieces of it? And so if I have one piece over here, I bet I might have the other piece over here. Never touches this vertical asymptote here, and never touches this horizontal asymptote here, and goes off that way. And so this is a part where basically practicing and using your homework is going to help you out. What I will say is, when you're working homework problems, after you try this by hand, check yourself with the calculator and learn as you go along. And remember, this part right here where we actually sketch it, we're just trying to see. We may have to make some corrections, but we have a lot of stuff to use, and we should be able to come up with some pretty good graphs.